Hi, class. Good morning. Can you hear me?
Yes, sir.
All right, that's great. So we had just the review of what we had last week. So to start this week, we are going to have our discussion for this first session for the week about compound curves, and next session will be about reverse curve, and in the third session will be again model quiz. All right. So we start today about compound curves. O kasi we are going to identify the elements of compound curves and then apply some problems related to the curve. In the actual, uh, as similar to the simple curve, it would be quite easier to locate the points if you are starting from scratch rather than having like modification or expansion of the roadways. Still, this is like two simple curves being connected. All right, so it's a combination of two simple curves. So if you can do it in the simple curves, compound curve could also be done. But the complexity here is you already have two different radius combined in the curve. For what reasons, or whatever reason that you have, that is because of trying to at least get the comfort of the user or the driver. Okay, so as I've said, this is a combination of two curves. So that means you have two radius, okay, with different degrees of curve. Of course, when you have two radius R1 and then R2, your degree of curve follows also with two different degree of curve. Again, the degree of curve is the central angle uh, with respect to the station. So our station is a 20-meter station, okay, 20-meter interval. So it is used when there is a space restriction. So meaning you have the restriction in terms of mobility of your curve. So you need to adjust by having two different curves. Now the formulas are established coming from the simple curves. It's only applied to compound curves. So key points here, you have two or more consecutive simple curves. You have different radii, or radii is the plural for radius. All curve centers lie on the same side of the curve. Okay, you have, like the reverse, they are in the opposite direction. The consecutive curves share a common tangent because, for example, you have here, this is the tangent to the first one. This could be the tangent of the other one. Then here's another tangent. So you see, this one is the common tangent. All right. For example, you have tangent 1 here. This is also tangent 1, but this one is tangent 2 already. Tangent 2. So in other words, the common tangent is T1 plus T2. Now, if consecutive curves lie on opposite sides of the common tangent, then that becomes reverse, which we are going to explain and discuss next meeting. Now, the point of compound curvature, this is point of compound curvature, because this is a compound curves. This is the point where connects two curves, I should say. Point of curvature, point of compound curvature, and then you have a point of tangency. We have drawing here later. Okay. So you see here, you have your I1, or the intersection angle, which is also the central angle of the first radius. You have to take note about it. Again, and then if you have like, this is the long chord, all right, or the first curve, then it follows that this one is also the deflection angle, which is just I1 over 2. Again, what is deflection angle? That is the angle that we use to locate this point. Every point has its deflection angle, meaning it deflect from this tangent. Okay. So similarly, if you have here I2, because see, if you are going to extend here, this is I2, right? Extend this one. No, sorry, this one. This is your I2. That is always the intersection angle between two tangents. Tangent and then tangent, the intersection is here. So it's the same here, it's I2. And this is also the central angle. All right, and then if we are going to connect again, it's long chord for the second curve. Then this is also I2 over 2. Now, this intersection angles, if we project this line, becomes the intersection angle of the compound curve, which is I1 plus I2. All right, you have here the second radius, which is also here, R2, only coming from here, okay? R2 is only from here. But R1 is here. The same with this one. Hope you can follow. The formulas are the same, okay? I just have to use accordingly with your calculation. For example, T1, then we use radius 1. You use the intersection angle for the first curve. Similarly, for tangent 2, you do accordingly with the second curve. All right. So let us have this example. You are to compute the length of the common tangent of the curve. So, as I said, where's the common tangent? This one is the common tangent. This is the common tangent, T1 and T2. Now, given here, I1 is 24 degrees, I2 is 36, D1 is 6, D2 is 4. You have to compute the length of the common tangent. You have to compute the station PCC. PC is given, and then also station PT. So here's the angle or the given figure, okay? This is a problem. The given figure is here. PC is given to be station 10 plus 420. I1 is 24. This is 24 over here. I2 is 36 here. You have T1 and then T2. That means common tangent is T1 plus T2. This is for letter A question. So starting from the first curve, R1, we can use this formula 11.45.916, or we have the formula of this one is like 3,600 pi d, right? But you can use this one either way, because 3,600 divided pi is 11.45.916. We are computing for the first radius, then we use the first degree of curve. We have this one as our radius of the first curve, and the radius for the second curve is bigger. You have 286. So this is the second curve, this one is the first curve. Common tangent, as we say, common tangent is just equal to T1 plus T2, right? This is T1, this is T2. Simple substitution. All right, R1 is here, substitute here. I1 is, this one is 24 over 2, that becomes 12. Whereas this one is 36 divide 2 gives you 18. So this is the common tangent. Quite easy, okay? Now, station of PCC. Station PCC is already given. Okay? According to the problem, this is 10 plus 420. Now, this is going here, is the length of the curve 1. If we can get this one, then we just add length of curve, then we can calculate PCC. That is why you have here, this was the calculated length of curve, L1. LC1 or L1 is fine. This is the formula. 20, I1 is 24. We can have the length of curve, the first, going here. We can locate PCC. 420 plus 80 is 500. By the way, class, you might ask, what is this 10 plus 500? This is just equal to 10,500 meters, okay? That's what's this? The standard in roadways. Okay, you can commonly see stationing like this one. Okay, let us see. What is the station PT? If we have PCC, which is already given, PCC is 10 plus 500. PCC is 10 plus 500. How about length of curve 2 or LC2? 20. What is I2? Should be I2. I2 is 36. What is D2? D2 is 4. All right. What's the value of this one? 5 times 36. 180. In other words, station PT, which is already here because we already have PCC, you add over there your length of curve 2. Then you have 10 plus 500 plus 180 will give you station PT is 10 plus 680. Any question, class? Easy, right?
Yes.
Easy, doctor.
Okay, I hope. All right, if you have some clarifications, just don't hesitate to ask me, okay? All right, you can interrupt me while I'm discussing. Okay, how about sample problem number 2? What is this? Chords or the chords of compound curve from PC to PCC and from PCC to PT are 130.6 and 139.16. This is the one, huh? Sorry. PC to PCC, 130.6. PCC to PT is 139.16. Going here to here. This is the chords of this is curve number 2, and this one is curve number 1. All right. Its common tangent makes an angle of 20 degrees and 36 respectively. So you see here, 20 degrees and 36 degrees respectively. So you start first. This one, PC to PCC, comes first. All right. The last one is 36. This one is, okay, for the curve 2, curve 1. What comes first here is the curve 1. Okay. You might be confused because usually this one is not given. Okay, the figure is not given. Now, with the tangents at PC, okay, determine the length of the chord of the compound curve. It is the chord of the compound curve. This one, right? Going here, up to here. Okay? This is the length of chord of the compound curve. All right? So, how are you going to calculate it? Okay? So, if you see here, this is a formula, right? This is a formula of your chord. If you remember what's this? You remember in our first meeting about the simple curves. You have this formula. This is length of the chord. So, for example, in the first curve, you have, this is the chord of the first curve, 130.6. Of course, this is the first curve. You use here radius 1, and then I1 is 20 over 2. You can have radius 1. All right. Now, the radius 2 here C is 139.6. It follows that you have also here reduced 2. 36 is given. You can have R2. These are the radius or the radii for two curves. Okay. Now, what we are going to calculate now is this long chord. Okay. Long chord. This one. Okay. Going here. But we need this A and B. This is the long chord that we are trying to calculate. The cosine law, we can use it here by cosine because this one is known. This is radio 1. Oh no, this is our chord 1. This is chord 2. It's already known. But we need to calculate inclusive angle. You remember in your trigonometry, the cosine law? For example, you have A, B, C. This one should be the angle C. Angle C. You can calculate this one as like C squared, A squared plus B squared, right? You remember? 2AB cosine angle C. For us to identify angle C, then we need to calculate what is A and what is B. A plus B is the total angle, inclusive angle here. So, for example, let's consider first radius 1. Where's radius 1? This one. Okay. If this is radius 1, this is also radius 1, right? Because this is the center of the, this is the second, this is the first curve actually. Okay. This is the first curve. This one is radius 2. So, for example, this one, R1, we have R1 squared. The two sides, R1 squared and 130.6 squared. Can you follow? Then, using this formula, okay? For example, this is R1. This is also R1. And this one is 130.6. Using this formula, we can substitute here. B here could be the angle C. Okay? You follow? So we can calculate here B is 80 degrees. So this one is 80 degrees. Now, similarly, if we consider the second curve, this one is the first curve. You have also here, I will try to figure out here. Okay. This is R2. This is also R2. This is the chord which is 139.16. And this is A. So R2, we can use this formula. R2 squared. This one is also R2 squared. Plus 139.16 squared. Minus 2. This one and this one. Then angle A, cosine of A. So therefore, we can calculate A. Do you follow, class?
Yes, sir.
All right. So once you already have A and B, then this long chord of the compound curve will be calculated. See, for example, the formula is, I will write here, the formula is C squared. This side is C2. It's the chord for the second curve. Plus, this one is C1. C1 is squared. Minus 2, C2, and C1. Right? Cosine A plus B. So you have here C2 is 130.6, C1 is 139. All right. The drawing is not just proportion, okay? Then you have substitute here. A and B, we already have the value earlier. That is 80 plus 72 is 152. Therefore, we can calculate the long chord of the compound curve. Compound curve, okay? Long chord of the compound curve. That is from PT to PC is equal to 271.76 meters. Why are we calculating this one? Again, as I said, these are the elements of the compound curve that we need to determine in the actual. Because in the actual, there are a lot of obstructions, like there might be some trees here. So you need all these elements that would help you locate the points in the curve. Another question, class, for the second problem?
No, no, sir. All clear.
If you have questions again, anyway, this is recorded. You can go back to the recording. If you have questions, don't hesitate to interrupt me. Okay, let's go to the sample problem number 3. You have common tangent AB. Where's AB? A, B. This is T2. In other words, this one is also T2, right? This is T1. In other words, this one is also T1. The distance of that common tangent AB is 76.42. So from here, going here, is equal to 76.42 meters. All right. The vertex V, this one, being inaccessible because there might be some, for example, there might be some trace here, okay? Now, the azimuth of tangents AV, where's AV? This one, huh? AV. What do you mean by azimuth? This is 247.5. Where do you measure the azimuth? This is north, this is south, this is A, going there is V, right? According to the problem, the azimuth is 247. Azimuth is always measured coming from the south. So this is 247. You have to check, all right, the location. Going here, the 3/4, that makes 270. So you are correct. This is 247. Now the other one, VB, this one, is the azimuth is 282. It's going here. That's why it's correct, okay? 282. Going here up to here is 282 minutes. Now, the stationing at of A, where's A? This one. The first intersection, point of intersection of the first curve. We again, as I said, compound curves here has two curves. So the first point of intersection, the first curve is at A. The station is 43 plus 10.46. The degree of the first curve is 4 degrees, meaning this is D1. That is based on the 20-meter chord. Now, using chord basis, take note, chord, not arc. Determine the stationing of the PC. Now, what is I1? Where is I1? This one is I1, right? AB has an azimuth as well. Okay? AB going here up to here is, what's this one? 268 degrees, 30 minutes. While AV going here up to here is 247. Meaning 268 minus 247 will give you I1. Alright? That's why you have I1. 268 minus 247 minutes. We have I1. How about I2? The same approach. Okay? I2 is this one. Again, you have 268. 282 minus 268. 282 minus 268 becomes your I2. I want you to figure it out, but you just have to measure. Okay. I'll do here. I2, this one, right? I2. It should be like this. Here is 282 from the south. Going here is 268. That's why you have here is your I2. Okay? If you're going to plot this one in AutoCAD, it will be easier to identify. But you have to read, okay? You have to read. But sometimes figures are not given. All right. Once you have your I1 and I2, it would be now easier to compute for, let us say, a radius of the first chord. Now take note, chord bases. You remember this chord bases? You only use the chord, not the arc. Exactly from this triangle, it's easy to derive, okay, using sine function in a trigonometric function identity. Sine of d over 2 is just equal to 10 over r. That's why if you use d1, you have this one, and then r1. So r1 could just be easily calculated. Once you have your r1, this one is already known, then you can calculate t1 using this formula. r1 tangent I1 over 2. You have t1. Now, the question is, now, station of the point of curvature is given. No, is to be calculated because this one is given. The point of intersection at the first curve is given. If you subtract this one by T1, that will give you the station PC. That's why you have 43, okay, plus 0, 10.46 minus 52.25. That's 52.25. That is T1. Meaning you're going back, okay? So that's why you minus. So it is just like when you use it in calculator, you just type 43,010. So you just write in the calculator 43,010.46 minus 52.25. It will give you 42,000. You just separate it with the plus 958.21. Now, determine the tangent length T2. T2 here is easy to calculate already because you have the common tangent, okay, is equal to T1 plus T2. Common tangent is given, okay? Common tangent is given. That's why you have T2 is equal to common tangent minus T1. Common tangent is already given, 76.42. It's given in the problem, okay? This one, all right? So we can calculate T2. What's the question, by the way, again? The last question, PCC, you have to calculate and then PT, okay? Once you have T2, everything could be calculated. So station PCC, this one, is just equal to PC and then length of 2. Okay? Station PC and then length of 2. Here, over here. No, length of 1. Length of curve 1. Okay? From PC plus length of curve 1 will give you PCC. We already calculated earlier T2. We can also calculate radius 2. Using this formula, we have T2, can calculate R2. All right? So, the length of curve 1, using this formula, 20 I1 is already calculated. D1, you can get, okay, length of curve 1. From PC, which you have calculated earlier, this is PC, right? You add the length of curve 1, L1, this one. Then you can calculate PCC. Now, to calculate PT, okay, it's just PCC plus, how about here, going here? It's length of curve 2, right? So, length of curve 2 is equal to 20 I2 D2. I2 is given, D2 is given. You have length of curve 2 is 48.1. By the way, earlier, we just calculated here D2, which is 5.58, using the chord again, okay? Chord basis. So that's why you have here D2, which is 5.58. Once you get the length of curve 2, you just add it to PCC. PCC is 43,061.55, which we calculated earlier, this one, plus length of curve 2, you can get station PT. So this is the summary of your answers. Other questions, class?
No, sir, all clear.
All right. I hope it's everything's fine for the rest of the class, okay? All right. I can give you one last more sample. So we have here a long chord from PC to PT. If a compound curve is 300, it's clear from PC to PT is 300. Now, the angles it makes with the longer and shorter tangents are 12 and 15. 12 and 15. Okay. This one is the longer tangent. According to longer tangent is this one, meaning the first curve, and the shorter tangent, this one, is 15. Now, if the common tangent, if this is the common tangent, okay? If this common tangent is parallel to the long chord, find the radius of the first chord, R1. Then find the radius of the second chord, all right? And then find the stationing of PT. What would be the stationing of PT? Okay, when you calculate R1, you can also calculate length of curve 1, all right? You can get to this point. And then from here, you add length of curve 2, you can calculate PT. PC is already given. So PC plus L1 plus L2 will give you PT. Now, how you're going to calculate first radius? You have this triangle already. Okay. Now, here is 12 degrees. If this is 12 degrees, this one is also 12 over 2. That's why I1 over 2. This is I1, okay? This is 6. In other words, this is also 6. Now, deflection angle, either from here or here, 6. This is also 6. Since this one is parallel, if this is 6, this is also 6. Okay? This is 6, this one is also 6. Why? They are parallel. For this case of compound curve only. All right? This is 6. It doesn't mean that this is also 6. But here, this is parallel. This line is parallel with this one. So similarly here, you also have R to 15. So in other words, here is 7.5. 7.5 degrees or 7 degrees, 30 minutes. Why? 1 degree is equal to 60 minutes. Okay? 0.5 of a degree is equal to 30 minutes. That's why you have here 30 minutes. Okay? This is 7 degrees, 30 minutes. In other words, this is also 7 degrees, 30 minutes. So therefore, we have this triangle. Okay? You have this triangle. 300. This one is 6. This one is 7.5. What do you think is this one? We play with these given figures because here this is the chord of the first curve, the chord of the second curve. Once you can calculate this one, then you can calculate R1. All right? So, as you see here, if this is 6, this is 7 degrees 30 minutes, it follows that this one is 166 degrees 30 minutes. Why? The internal angle, all the angles of the internal is equal to 180 degrees. 166 plus 6 degrees plus 7 degrees, 7.5 degrees is equal to 180 degrees. Okay? Do you follow with me? Now, it's easier now to calculate this AC and BC. Just sine law. For example, 300 opposite which is sine of 166 degrees and 30 minutes is also similar to BC or proportion and then the opposite. That's why we can calculate our BC. Here we can also calculate AC. Once we have BC and AC, then it's easier now for us to calculate the first radius. Okay? What is this? This is triangle. Okay? If I'm going to look at this one, this is 90 degrees. Okay? They are equal. This is T1 and T2. They are equal. Okay? So you have this if I'm going to derive from here, okay, sine I1 over 2 is equal to the opposite, which is this one, this side, which is AC over 2 divide radius 1. That's why we have this, okay? So, cross multiplication, this is 6 degrees, okay? We substitute, we can calculate R1. Do you follow, class? This one is clear, right? It's simple mathematics. I don't think it will be difficult for you. Now, for this one, okay, this is right angle. This is BC over 2, right? This is R2. This is I2 over 2. That's why you have here sine I2 over 2 is opposite, which is BC over 2 over R2. That's why you have this calculation of R2. You have R1, you have R2. We can calculate now L1 using this formula. We can use this formula. And then L2. Then we have PC plus L1 plus L2 will give you station PT. Don't you worry about this one because these are already formulas, all right? What you need to do is just to be consistent. If you're calculating length of curve 1, you can write LC1 or L1. It's fine, okay? This is radius 1, angle of intersection 1, pi, or 180. All right? Other questions, class? Hello, are you still there?
Yes, sir.
Okay, let me check your attendance. Who's here? Before we dismiss our class. Hopefully you started already your assignment. Wait for a while. Check. Let me just check your attendance. Abdul Karim, not here. Fatima is here. Fatima. Salman Ali, yes, here.
Yes, present.
Some of you already recorded the attendance. I'm just checking those who haven't had attendance. Syed Rida, still not here. Okay, so that's all for today class. Do you have some concerns that you would like to speak out? Like to
Doctor, can
address?
you mark me present?
Yes. If I didn't call your names, I already checked earlier.
How about
Yes,
me,
Dr.
Doctor?
Ahmed didn't call my
Yes, you're present. I already see it in the list.
Present, Doctor. Sure?
Yes, I already I've seen it already in the names of yeah, Ishraq, you are here, okay? Don't you worry.
Okay, thank you,
The
thank you.
the last names that I have called are the ones who were missing in the start of the class, okay? So if you have no questions, you are free to go. I want you to start now with your assignment so you don't get rushed, okay? Welcome, welcome. See you. See you
Thank you,
next
thank you,
meeting.
thank you.
Okay, inshallah.
Thank you,
Bye-bye.
doctor.